Our second speaker today is Dave Kelf, who's the VP of Marketing for OneSpin Solutions. Dave's based in Boston today. He's going to be speaking about leveraging exhaustive formal analysis for security verification. Dave heads OneSpin's marketing efforts, including technical and product strategy. Dave was an IC designer before moving to application engineering and general business roles. He is president and CEO of Sigmatix Incorporated and verification marketing director at Cadence Design Systems. As vice president of marketing at Co-Design Automation and then Synopsys, Dave oversaw the successful introduction and growth of the System Verilog language before running marketing for Novas Software, which became Springsoft and now Synopsys. He holds a Master's of Science degree in Microelectronics and an MBA from Boston University. Very impressive, Dave. We're going to hand over to you now.
Oh, thank you, Mike. It's been a long introduction. Well, I hope you can all hear me. I've got a bit of noise on this end, but let me know, Sarah, if there's a problem. An excellent presentation by Paul there. What we would like to do is talk a little bit about some of the ways that we've seen formal be used in the security space to date. Including some work that we've done with our partners, Tortuga Logic, who are security experts, especially based in San Diego, working in this area. And we're obviously focused more on hardware security than software, although, as Paul mentions, the two overlap quite a bit. So firstly, just to review again, some of the ways that we've seen people trying to get access to secure areas. In many of these designs, you see a number of sort of possible sources, which I believe a lot of engineers are. It's quite unexpected. So some of the ways that people can get into these devices these days, although most companies have a number of security experts who are very familiar with this, there are a lot of general engineering efforts going on where there's less experience in security, and those can lead to a lot of different problems. And these are just some of the ones that we've seen. Backdoor access to secure areas on devices, usually through things like scan paths or debugging type modes of operation, which have been left in either purposely or accidentally. We've certainly seen some of those. Scan path is a very typical one, and I know we've done quite a bit of work to secure scan path access to secure areas on devices like protected keys. Also, access via some unexpected operation, that is setting a state bit in a design, for example, which was unexpected that it could actually even occur at all. And this is a classic thing where you can get into part of a design which may have nothing to do with a secure area on a device, set a state access that allows a bus read and write, which otherwise shouldn't occur, into the secure area. And then gain access to some important aspect of it. And this has been used, we believe, by people trying to derail chip operation. And the automotive space is a classic example, and one of these was actually identified to cause some of the problems we've seen recently with cars being driven off the road by hackers. As Paul mentioned, side channel attacks is a key one. Watching for specific operations on the device, like a key access, and at the same time inspecting the power rails or some other aspect of device operation to understand if the key can be read from that. And Paul showed that very well. This is something which formally it's hard to verify, of course, because you don't usually go as far as the power rails, but you can do it if required. Software application vulnerability. So a classic source of errors is where a software application, even working in maybe a secure virtual machine on a device, can perform a function such as overflowing a buffer and then being able to read the buffer and find an illegal address space, which can then be used to access against some secure area. There's another classic problem, and there's an excellent couple of papers written about this and how people are using it and how to protect those kinds of software vulnerability. And then a classic that I think Paul mentioned as well, inserting something like a Trojan horse during the fabrication of the device. Harder in ASIC design, but for FPGAs and FPGA design, this is becoming quite a common thing, and it's something that the DoD, the Department of Defense in the US, is particularly concerned about, given the number of FPGAs used in defense applications. So they put specific mechanisms to check the bit streams of the FPGAs as they're being uploaded into the devices, and of course, companies like Microsemi with their their flash FPGA ROMs on their devices try and protect against this particularly. So of course, as we all know, many SoCs usually incorporate, or often these days incorporate, a protected region on the device, and the classic example is the ARM trust zone mechanism, which essentially ties a secure area or a trust zone area on the device to a secure virtual machine, and the virtual machine in the software world can only get access to that secure area. General applications cannot. And this is obviously a very effective way of handling some of the software to hardware security problems, but the hardware still needs to be verified against backdoors and issues like that. So this is something that formal verification obviously can be used for very effectively. There's two overall types of vulnerabilities that we see. The integrity vulnerability is one where some access is gained to a device and puts it in an operational mode that was unexpected, and therefore creates a critical problem, maybe in some area which is not it should not be targeted. And this can happen maliciously or quite often accidentally, where maybe some device in, say, a paging system, a pacing system, a heart pacer, actually gets interrupted unexpectedly. And this sounds a bit fanciful, and actually there's a series in America called Homeland, where the vice president of the country was targeted using a system like this, and everyone kind of chuckled and said, yeah, is that really true? Yes, actually it can be done, and has actually been done in some places, even though it seems a nasty thing to do. So these are very unexpected types of problems, and it's something that definitely needs to be protected against by basically siloing parts of the device that's being used. The other, of course, is confidentiality vulnerability, and a perfect example of this is trying to get at a secret key somewhere on the device and getting it to some untrusted output so the key can be read. And we've obviously spent some time talking about that already. So, Paul mentioned that the use of formal verification is key nowadays to check these secure devices. And of course, the reason for this is if you've managed to set the properties up correctly to check for specific things, then the formal tool will exhaustively check all the states around that property to make sure that that property either holds or does not. And this is an ideal thing for security because with the kind of complexity in the devices we're seeing now, the possibility that either some strange state was left in there which is unexpected, or that an unusual state of operations can be inspected to find a key is very possible. And again, I suspect most of you know this, but of course what simulation does in general is, based on stimulus, find a path through the state operation of a design. And what you hope with simulation in general is that you generate enough stimulus so you check all the states of concern in a design to make sure that that no bad operations can occur that would be unexpected. With formal, what you do is, for a given property, check all the specific states in one cycle. The disadvantage of formal in general is that the amount of cycles that you can test, of course, is restricted based on the capacity and the performance of the tools and the machines they're running on. So it's not a panacea, unfortunately, for doing this, but for security, often a lot of the types of issues that we see will occur in a restricted, bounded set of cycles. Even if it's a few hundred cycles across a large device, that is possible to test with a formal engine. So, as I think you touched on, Mike, in your last question, although formal generally is used on a block level and for specific areas of an SoC, by abstracting carefully and constraining parts of the chip, we can use it across now a very large device, and we do see people doing that today in different areas, especially in the safety and the security areas, of course. So there's really three things that formal is particularly good at, which can be used very effectively for security analysis. Firstly, signal propagation is a key aspect for security, trying to get some aspect of the device, a signal, something like that, to propagate to some access point, be it an output pin or an unexpected write to a memory on the device or some other thing like that. can be checked very easily with formal, and the kind of propagation paths that you see can be quite unexpected and surprising. So this is a key aspect of formal, which is very useful. The second thing is, of course, hackers will often try to set states inside the design which are both unexpected and often unverified, to then make, to then allow for a bad read or a write to get access to a key or some other operational aspect. Again, formal verification can be used to check how a lot of states are arrived at, and for any bad states that might have actually not been purposely created in a device, so it's extremely useful. And the third thing, of course, and a well-known use of formal is the comparison, including the sequential comparison of different blocks to make sure malicious code or malicious hardware is not placed into that block. So if we look at a device, where is it that formal can be used, and what kind of properties can we create to actually allow, for a full secure check of a device? The classic one, of course, on the right-hand side is checking for the access of a key onto any outputs of the device, and this might be include outputs such as scan paths, or debugging outputs, maybe a multiplex debug mode on the output of a device which was either left in accidentally or not disabled properly. And this is probably the most common type of security vulnerability that we've seen in use with these tools. So basically, a property is written that checks the propagation of a key to any output that will be seen in sec, and that output is then analyzed to understand the path from the output back to the key to make sure the vulnerability can be removed. A similar one to this would be a write of a signal from a secure area into the cache of a processor, and then from there out through a software application specially created to go after this. That's another one where it can be tested fairly easily with a formal property for checking bus read and writes that might be created through unusual states. Checking that no input path exists from either a pin or from the bus into a secure area, again, is another key one. Basically, a property can be written that attaches, it basically says, can this particular state be arrived at from any input path, and that will reveal a lot of potential problems there as well. So there's a number of these different properties that can be created that attack the secure area and device. And again, looking at devices, say, that make use of the ARM trust zone mechanism, it's possible to get a backdoor maybe into the secure hardware area, and then from there, through into the secure software and can cause all kinds of damage. So checking for these different security issues in that secure area is absolutely key. And this is really the focus, I think, of the formal tools in this area. So something that we've been doing is working with a partner of ours, Tortuga Logic, and this is a company that is specialized in performing different security checks on devices using the formal engine underneath. So what they're able to do is basically understand, read the RTL code, check a very sort of high-level property that targets a specific area of the device that needs to be analyzed for security issues, and then create formal properties and run them on the formal engine to make sure they can't be targeted. So, the two guys gave me an example here, a very high-level example of a device that they actually worked on not that long ago. It was one of the top semiconductor companies around. It was actually an FPGA company, and they had a platform where they wanted to check for a key register, and could that key be accessed anywhere on the hardware. They'd already tried to visually inspect this device and were fairly sure that it was fairly rigorous in terms of security, but nevertheless, wanted to really make sure. So they wrote a property, and this is kind of how one of these high-level security properties is created that targets formal. So essentially what it says is, can the key not flow, and this is their nomenclature for not flowing, the equals/equals, to all outputs, ignoring the AES connection to all the outputs. I.e., they wanted this any key to be flown to the outputs through the AES encryption block on the device. And what they want to do is make sure it couldn't flow to any other outputs. So a pretty high-level sort of property to basically specify that. And essentially, what they could do is take this key and essentially generate system Verilog properties that would check all the outputs, including any possible multiplex debug outputs onto one of the main pin outputs, or the scan path, or other areas inside the device, the interconnect up, so that the key can be read into memory or anything like that. So essentially, the property spawns out all these other system Verilog properties, which is run on the formal platform. And the other nice thing about formal is that if there is a assertion that doesn't hold, a witness can be generated, a counterexample trace, which shows the path from the vulnerable area right to the output, and makes it very clear what can actually create this kind of problem. So, a witness can be generated which shows the path of the key through to the output, and whichever enables and modes have been set to make that happen, including malicious modes coming in on the input. And in this case, of course, there was in fact a vulnerability where a debug mode had been left in the device that was unexpected, and there was a path from the key to one of the extra outputs, not through the AES, when the device was being booted. And this was a big issue because, of course, it's often during the boot process or some other aspect of a device like this when these kind of vulnerabilities are apparent, and it's a combination of the boot process in this case and of the debug mode that was left in there that created this problem. So this was a very real problem inside the device, and was easy to fix once it was understood, but almost impossible to spot through any mechanism except for using a formal type of approach to the problem. And a second issue, and this is actually a block that was based around the OR2 open cores library, and essentially there's a encryption module on there which will take some data and a key and use that key to encrypt the data, but this encryption takes 500 cycles. So what the Tortuga guys did is took this piece of code and just did a quick analysis to see if there was any way that key itself could be output to the data out in an unencrypted form, which then would allow a hacker to then get any of the data that was being passed through that encryption. And in fact, when they ran it, using the property above again, very simple property, the system failed in 4 cycles. Even though it's supposed to take 500 cycles for the encryption to be processed. And what turns out happened is the key was XORed with the data, and because the encryption process hadn't fully run, the key was apparent on the output, but it was actually well embedded inside the data. So it was very hard to spot and tell that that key was out there. But with a formal tool, what you're able to do is, if you like, multiplex or extract the key from the data and spot that coming out. So this is another use of formal where if you just look for a key and can it be placed on the output here, it will extract it from other data which otherwise might not be immediately apparent. So they did this and basically tried to reset the output using basically an AND gate to make sure that if the ready signal was set, then only then could the data be read. A pretty obvious enhancement, really, but again, needed to be added there, and was only apparent because the key was interlaced inside the data. So after this, it takes 506 cycles for the encryption to behave and to run, and then after that, the key is basically encrypted inside the data. So it's okay that it's actually on the output after that. Again, it's a simple case study, but it shows that a simple property here and there can actually spot very complex issues and problems. The other issue that we mentioned at the beginning is one of Trojan horses being inserted inside FPGA bit streams. And again, this is an issue which the Department of Defense in the US has been particularly concerned about. And we've been working with Macaulay Brown, one of the larger defense contractors over here, on mechanisms to help prevent this being done. FPGA design, of course, is particularly susceptible because it's possible to get at the bit stream of the FPGA and insert something into the bit stream, after place and route, which can cause a problem. And equivalency checking, of course, particularly sequential equivalency checking, can be used to make sure that functionality has not been inserted, which will cause this kind of problem. And if I show you one of these slides, this is an actual Macaulay-Brown slide of their system to do this. The classic vulnerability happens when an existing FPGA design is ported to a newer FPGA device, and this is something that they've seen more than once, apparently. So what happens is the original silicon and the bit stream which drove that original FPGA silicon is translated up back to some hardware tools to allow it to be resynthesized, which is a standard mode of most of the large FPGAs. So Macaulay-Brown actually has a tool which handles this whole process and then retargets the bit stream to a new device. So vulnerabilities exist if this process is being performed by a third party, possibly with folks there, and remember these are DoD type devices, so folks there that are trying to get into the device. What they're able to do is sometimes use even the original FPGA tools to extract the design, insert something else, and then retarget it to a new device. At other times, it's possible to actually go to the bit stream itself, avoid all the design tools, and insert some additional bits into the bit stream, which can affect the device itself. So what Macaulay-Brown does is use equivalency checking to essentially check the actual bit streams together after all the tool fabrication and the place and route has happened, to make sure the bit stream is not altered. And this is a key use of formal. And you can see that Paul mentioned in his presentation other areas where extra code can be inserted inside a design. So the use of sequential equivalency checking at the RTL level, or the RTL to gate level, or even at the bitstream level, can be a very effective way just to do that final sign-off of the RTL code and to make sure that that it's not changed or modified in any way before it goes on the FPGA. Once the code's on the FPGA, it's extremely easy for a hacker to gain access right across the device and do all kinds of things. So this is the other way that we see formal being used quite successfully in this. This is, as you can tell, it's a fairly high-level presentation just to sort of provide a quick 20-minute sense of methods to use formal verification. But there is various details on the web on how how these properties may be created and the specific kinds of attacks that can be used. So hopefully this just gives you a sort of a broad brush sense of what's possible here. And so, of course, OneSpin provides all these kind of features, as you'd expect. So that's the end of my presentation. I'm happy to take any questions.
Okay, thanks, Dave. Hi Dave, we've got one question from Bristol.
Okay. Hi. Yeah, I've got a couple of questions actually. First one's really on the practical about the actual properties that you produce. Do you set the key or the bit of information that you want to be secure? Do you set them to X and then look for propagation of X's? Is that how you actually check for propagation of? Yeah, that's a great question.
And you can certainly do that. So some of the early formal security mechanisms did exactly that, right? They basically create an unknown state, which at the RTL level, as you say, can be an X state, which can be clearly identified against ones and zeros and high impedance and what have you, and then would test to see if that X would propagate to the output. And that actually works quite well at a basic level, but falls down, of course, if you've got a design where there's other unknown states or other uninitialized states. And the problem with a lot of the security vulnerabilities is they tend to occur during reset or reset phase. So the device is reset, and that's when some of these devices problems emerge. So we found that just using X propagation, while it was useful for general operation, was not helpful during the reset phase. So what these properties do is use free variables or other mechanisms to identify where the key is and the path from the key from the output. So it uses other mechanisms than X state propagation, but it does use propagation techniques.
Hi, David. It's Mike here as well. I presume if you're doing X propagation, you do have to control logic set to the right values for the X to propagate as well, which formal would be more exhaustive than that.
That's correct. Yeah. So and that part of the problem is figuring that out, right? Because the vulnerability occurs not just because of the propagation, but because the propagation happens usually during some unusual state. So from the inputs, or maybe a debug input, or a JTAG, scan path, enable, something like that. A state is set up so that the key or the state that you want to analyze makes it to the output, right? And as I say, the problem is that often happens during reset, and so you need to be testing the device in the reset phase. And if you do that, then other X's couldn't be floating around. So then it can interfere with the specific propagation. So there are better ways of doing it than just setting an X to the device. We can set special values and other indicators to check the propagation, or we just analyze the propagation paths without actually looking at a value that's being propagated. If that makes sense.
Okay. Thanks, David. Anthony's got another question.
Okay, so you're talking about having backdoors through the scan path. Now that's obviously inserted during synthesis. So are you saying that we should be running these formal on gate level post synthesis rather than on RTL?
Yeah, it's a great. Yeah. So unfortunately, yes, that's true. And you're right. The scan path is inserted during synthesis and sometimes even after synthesis. So a final check of a device, is important. One way that, and that's a problem, because if you start putting large numbers of gates into the formal tool, of course the capacity becomes an issue as well. So then you have to constrain the general formal tool to just focus on the possible paths from specific areas to outputs. What's another point there? So one other way you can get around this is by using equivalency checking to make sure that if you are able to check at the gate level using the formal tools, that you can then backtrack up to the RTL level and do some checks there. So for the checks that may say involve checking for a debug mode or something like that that's left in, you can check at the RTL level and then check the RTL level is exactly like the gates, less than scan path. So for some of these modes, you can definitely do the work at the RTL level and by doing so allow for the capacity improvements you get from that. For some of these, there's no substitute but to work at the gate level. And in fact, some of the standards that Paul mentioned, as well as some of the the safety automotive standards, which are starting to include security as well, insist that you work at the gate level on the final design and not on any kind of abstracted form of it as well. So you have to actually work at the gate level to meet all those standards.
One more.
So if we have to not insert scan for this secure area, how do we test that in production?
Yeah. Well, so you do have to obviously insert scan. So the question is, and there's two things we've seen. One is that the after synthesis, that the scan path is set up so that it does not either access that register or the register is connected to it so that they can't actually put the device into some state and then switch the scan on, right? So you have to include some extra additional circuitry to disable the scan path. And there's actually quite a lot of work going on to sort of see how areas of the device can be excluded from the scan path based on security vulnerabilities. There's actually a very good paper on that. I can't remember what it is off the top of my head, but you can see that online. The other thing is to use the built-in self-test mechanism for the secure area. And a number of companies are doing that right now. So they'll create sort of a BIS which is purely focused on the secure part of the design, and then reports onto some part of the scan path, but it does not allow access for any secure keys to be placed on the scan path itself. And that's really the only way right now that we've seen that people are handling this.
Okay, brilliant. Thanks, Dave. A good answer to those 3 questions. Thank you very much. Thanks, Dave.
Thank you very much.